Ngalakin Khadijan Nyunga Boja.
About the transmission line model, but that will be a little bit too early to start the discussion of the tutorial 2, because when we move on to the tutorial 2, we are going to use the model to do calculations. But we just started it. We have not learned too much things from the chapter 2. So today in this tutorial, we are not able to start our tutorial 2 question discussions. So today we are going to focus on the tutorial 1 remaining questions. Actually, on last Thursday, we have discussed the first 3 questions of the tutorial 1. And today, we are going to try our best to finish as many as possible. And because you have already got some fundamental understanding regarding the 3-phase or the AC circuit calculation, so in our discussion today, I will try to speed up a little bit. Of course, if you have any questions during the discussion, please just feel free to raise your hand and ask me. I can stop or pause and give you more explanations, okay? So everyone, please open your tutorial 1, and we are going to start our class from the question number 4 discussion, okay? Okay, on the screen, you can see the share screen between the online students and the face-to-face students, okay? So this is our tutorial 1 sheet. Question number 4. We consider a load impedance of Z equal to J omega L. Okay, this is just a purely inductive load because J omega L. So this impedance doesn't include any resistance. So it's a purely inductive load, okay? And this load is connected to a voltage V. And let the current drawn be current I. Part A is asking us to develop an expression for the reactive power Q in terms of omega, inductance L, and current I from complete power consideration. A very simple question, but just in case some of you forgot the details regarding the calculation of the complete power. So first of all, in AC circuit, out of the real power, reactive power, apparent power, and complete power, out of these 4 power terms, the most important one is the complete power, which is vector, because the complete power can tell you the value of the other 3 power terms. So the most important thing is the complete power. So regarding complete power, mathematically, this we are using S to denote it, but we should understand this complete power is a vector. So in the, if you can see the solution of question number 4, you can see we are using a vertical horizontal bar above the S to denote this vector. I think this part is a bit confusion because if you talk about the vector, the complete power, in this solution, we are using the S with a bar above it to denote this vector. But in some cases, as I mentioned in lecture, we denote the apparent power using a similar notation, just like S. You need to understand the relationship between these 2 terms. S, the apparent power, should be the magnitude of the complete power. In other words, this apparent power S is actually the magnitude of the vector S. This is called complete power. The unit is what? VAR. What VA? Do we have the R? No. The R is for the reactive power. This is called apparent power. And its unit is also VA. Okay, this is just a relation between these 2 terms, okay? This should be very fundamental. We have known that. So, but normally, for the complete power, how to represent it by using the real power and reactive power? S equal to P plus JQ. This is a complete number. Its real component is the real power in the unit of watts. Its imaginary component, denoted by Q, is a reactive power. The unit is VAR, R for reactive power. Okay, so this is very fundamental. By the way, for this power, real power, we are using watts or kilowatts. And for the reactive power, we are using VA and the R to denote it, so as a unit of that. Okay, this is a formula. The physical meaning of it the components of the complete power. But what formula we should use to calculate the complete power? Very simple. There are only 3 formulas. For calculating the complete power, the first formula is Vi star. This star means conjugate. You should also notice in this formula, both of the voltage V and the current I are vectors as well. So we put the vector bars above them to indicate they have them both of magnitudes and directions. The first formula is just like that. How about the second formula? The second formula is, if you are using Ohm's law, the current flowing through a component in the AC circuit, this I can be represented by voltage divided by the impedance, then conjugate of it. And then this conjugate can be given to each of the 2 terms of the fraction. This gives you V by V conjugate divided by the Z conjugate. V by V conjugate is actually calculating the magnitude square of this vector, voltage vector, then divided by the Z conjugate. This is the second formula. Similarly, I'm not going to go through again. The third formula can also be derived by using the Ohm's law. The result will be, so current vector magnitude square multiple the Z. Very simple equations, but you need to notice, if you want to use the voltage to determine the complete power, you need to divide it by the conjugate of Z. But if you want to use the current to determine the complete power, the Z doesn't have the conjugate operator. Okay, so for this part, what we need to remember, I believe these formulas will not be given in the formula sheet, okay? So for calculating the complete power, this is important. VI conjugate, but you need to know V and I, this voltage current must be vectors, okay? Or this thing, be careful, the V is a magnitude of the AC voltage. Doesn't have an angle at all, and then squared divided by Z conjugate. Finally, current, same thing. So, yeah. So, yes, good question here. For all the power calculation, we must use root mean square values only. We should never use the maximum amplitude of the cosine function of current or voltage to calculate. Never. Always root mean square values. Thank you for your reminding. Okay. Okay, after we understand the background of this thing, okay, I'm going to wipe off this stuff and let's focus on this question. And in the question number A of the, part A of question number 4, we want to determine the reactive power Q, but from the viewpoint of the complete power. So our task is to determine the complete power. So what is S in this question? Because based on the question, regarding this given particular load, we know it's voltage, we know it's current. So by default, we assume the VI conjugate to calculate this one. This is the easiest way, okay? So VI conjugate. But it seems if you want to use this formula, you have to work out what is the relationship between V and I regarding this particular impedance Z. Can we find the other way to work out this thing here? I think it's possible. You can see in the solution, we are using the Z multiple magnitude of current square to do that. This is the third formula we mentioned at the beginning, okay? So this is the same thing. Give us the Z impedance multiple the magnitude of I square here. So what conditions do we have? So this gives us Z is, the Z impedance has been given, so we just copy it down. J omega L for the inductance, okay? And multiple the current flowing through, which is just, okay, see here. You can find the notations is changed. This with a bar above it is indicating the vector, but this I with that bar is actually the magnitude of this vector. And then let's just arrange these terms. J is the J, relative long. This is indicator of the imaginary part. And then except J, we have the omega by L by the I square. Then finish. This is the complete power consumed by this inductance, okay? Very simple thing. If you want to just go one more step to make the whole thing clear, you may assume the real component of that is 0 plus j by the omega Li squared here. This is the format of the P plus JQ. Of course, real component, in other words, the real power is 0 watts. And its imaginary part, the Q, be careful not including the J, okay? It's just the value of the imaginary part is omega Li squared. That is the reactive power consumed by this inductor. Okay, very simple thing, but you also need to note one thing here. Because this load is a purely inductive load, it's not able to consume any real power. So the real power consumed by this load is 0 watts. But its imaginary component, its reactive power, is non-zero. Get that? Okay, this is the first part. So everything okay, everyone? Easy, right? Okay, let's move on to part B. So, is it readable? Okay, part B is saying, so let the instantaneous current be IT equals square root 2I by cosine omega t plus theta. Okay, up to now here, regarding this instantaneous current IT here, its amplitude is square root 2 by I. So we should be able to understand the root mean square current for this case is just I. Because if you want to convert the maximum amplitude of the cosine function or sine function to the root mean square value, we just need to divide the amplitude by square root 2. After that, the root mean square value is just the I itself. Okay? Okay, so obtain an expression for the instantaneous power, PT, in time domain, of course. So into L, and then express it in terms of Q. I think this part is pretty simple. I'm not going to write it. Let's just read the solution, okay? Voltage. This is voltage across inductor. For this part, we didn't use any so-called advanced circuit analysis technique. We just used the important voltage current relationship of inductor part itself to derive the voltage across inductor. We can use this because in this whole circuit, we have one single inductor and nothing else. So the voltage across this inductor is just the voltage of the whole load. But in the future, if you see some questions which combines both of inductor, capacitor, and resistors, something like that, so be careful. This formula may not be suitable for complete circuit, okay? But for this one, we just use that. The voltage across the inductor equal to the inductance multiple the change rate of the current going through this inductor. So we just need to do the derivative of the current, multiple inductance, to get to the instantaneous voltage across this part. Okay. Easy? Yeah. So this part should be pretty simple. The next step, so calculating the instantaneous power should be just a product between the voltage and current. And then the solution is showing us the calculation should be very easy. So I don't want to spend time in the session to discuss such simple calculation, okay? And after this step, we derive the second step, which is given here. And actually for this step, we are going to replace the omega by L by I squared by the Q here, because in the part A, we have already derived the Q equal to omega multiple the L multiple the current square. So we are just doing a very simple replacement. Yeah, go ahead, please.
Do we have to memorize the trig identities?
Just the same simple thing. Sine Q alpha equals 2 by sine alpha cosine alpha. It's just this thing here, because in the first step here, we got sine by cosine only. This is this part. So we just divide 2 on both sides. You have to use the other formulas. I think we have some formulas given in the formula sheet, but let me double check that. So far, I can't confirm this. Okay. So this is pretty much everything for the question number 4. Very simple thing. So no problem. Oh, good. Okay. Now let's move on to the question number 5. Actually, these questions given in the tutorial 1 are pretty simple, right? Question number 5. We consider a single phase load. When we talk about single phase, that always means easy because you don't have to consider all 3 different AC circuit stuff. Okay, consider a single phase load with an applied voltage Vt equal to 150 150 is maximum amplitude, okay? 150 by cosine omega t plus 10 degrees volts. The current going through the load is 5 by cosine omega t minus 50 degrees. Okay, pause here, everyone. May I just ask you, if I want you to evaluate the power or complete power of this load, is this a leading case or lagging case? Actually, my question is how to determine if that is a power is a leading power factor or lagging power factor, or how to determine it. So we define the leading means the current leads the voltage as a leading. Or lagging means the current lags voltage. But in this question, based on the voltage and current going through the load, the phase angle for the voltage is positive 10 degrees. Can you see that? And the angle for the current going through the load is negative 50 degrees. Okay, this is nothing about this question. I just gave you some idea, okay? If you draw these two vectors, current and voltage, in the complete line, its current is negative 50 degrees. So roughly, given here, its voltage is positive 10 degrees, which is pointing to this direction. In this case here, is it leading or lagging? Is the current leading or lagging the voltage? Lagging, yes. The reasons, again, we mentioned many times in last week. We defined the positive rotation direction is going counterclockwise. In such case, current is behind the voltage because the angle is negative, is below the real axis, right? So in this case, we are actually getting a lagging case. For lagging case, if I want you to plot the power triangle, will that be something like this or something like this? So option 1 or option 2. Leading or lagging, you know this is actually lagging case, right? For lagging, current angle, lagging, right, is smaller than the voltage angle. Agree? But how did we define this theta, the angle of the power triangle? The theta was defined as theta what minus theta what? Yes, theta v minus theta I. Right? Yes, that's right. Because theta v is bigger than theta I, it's greater. So theta v minus theta I means a bigger thing minus a smaller thing. The result theta should be positive. If the theta is positive, of course, option 1. Option 2 is not right for this case. In other words, actually, before you really solve the question, you should have some idea regarding what the result look like before you really get the numerical answers. Okay? Anyway, this is the background information. Okay, let's keep going. So we have 3 parts, right? Part A, determine the power triangle. Okay, actually, I haven't solved that. Okay, now we can just draw the draft triangle, okay? So for the A, its shape looks like this. So this is our power triangle for part A. We have known this one from condition, right? And we have already known the angle is how much? 60. So 10 minus negative 50 give us positive 60 degrees. Okay, this is just the angle. The remaining thing are just the values of the edges of this triangle. So real power, P, reactive power Q, and we call this as the size of the other edge is apparent power. So normally we can write the magnitude of the complete power. Of course, this edge is actually the complete power. Okay, calculation should be pretty simple because formula has already been introduced in the first part. VI conjugate. Regarding voltage, you have been given the time domain cosine function for the voltage. Just convert that to the root mean square vector, the phasor form of the voltage. Divide the maximum amplitude of time domain cosine function by square root 2 to get the root mean square value. And that may be used as the magnitude of it. Angle doesn't change. If you got positive 10, we just copy the negative 10. Positive 10, positive. We just copy the positive 10 here. And then after that, we got the voltage vector. And keep going. Conjugate of the current vector. So same procedure. I'm not going to repeat again. After this step, we work out the numerical answer, which is given as 375 is 60 degrees. This 60 degrees is the same as the angle we derived here. Actually, you can use this one to double check if your understanding is right, if your answer is correct or not. Okay? Okay, this is about the phasor form of the complete power. But regarding this question, we want to know what are the values of the real power, reactive power, and also apparent power. Apparent power is pretty simple, which is just a magnitude of the complete power. So apparent power here is equal to 375. Again, what is unit of that? VA, right? VA. Always write the unit of your calculation to avoid losing marks. Okay. And regarding the real power and the reactive power, we just need to use the angle 60 degrees plus a known magnitude 375 VA to derive the values of the real power and Q reactive power. Very simple for you. I don't do that. So this real power is just 375 by cosine 60 degrees. And the Q is 375 by sine 60 degrees. That. And unit are just watts and VAR. Yes, great. VAR. Then finish. I leave the calculation to you guys. Okay. Okay, this is a question number A. Question number B. So please find the power factor and specify whether it's lagging or leading. So lagging leading has been determined. So this is a lagging case, easy one, right? You must be able to know that because in our future discussions and lectures, we know this and we use this many times. Okay, leading, lagging. And what is the power factor? Power factor is cosine theta. This theta is actually the angle of the power triangle is equal to actually cosine. If you know theta, you can use it here. If you don't know that, you can use the theta v minus theta I to determine it. Same thing. 60 degrees, so that gives you square root of 3 over 2. And then convert that to the decimal numbers. So, oh, it's my fault. Sorry. It's so stupid. For 60 degrees, it's 1. 1. Is when you give the numerical answers of the power factor, please always follow the lagging leading information. Otherwise, I will not be able to know what is the direction of the power triangle. Okay? So part B is solved. Very simple one. Part C. Please be very careful with part C of the question number 5 because in past 2 years, similar questions were given in the class test 1. Okay, just for the compensation. Okay, so in the question C, calculate the reactive power supplied by capacitors in parallel with the load that correct. That's the target. Okay, we want to correct the power factor from 0.5 to 0.9 lagging by adding one capacitor or multiple capacitors in parallel with the existing load. But in this process, we do not want to change the real power because by adding a new capacitor or inductor into a circuit, this will change the distribution of the reactive power only. They are not able to consume any real power, so real power will remain same. Okay, so this new capacitor will change the reactive power, the Q term only. So we want to change the power factor from 0.5 to 0.9. So let's find this free space. So for part C here, we want to change the power factor from 0.5 to 0.9, still lagging. So we know this power factor equal to 0.9 is actually equal to cosine the new theta, because that's a theta prime. This theta prime should be new angle in the power triangle, right? But because we didn't change the leading lagging thing, so this power triangle is still lagging. And the direction of this power triangle, I draw the original one first, okay? Original one looks like this. And this is theta equal to 60 degrees. This is the result from the first part. But now we want to change. Real part, P, remains unchanged. But the angle of this power triangle will be changed to something like this. This angle is a new angle. We call this as theta prime. the set prime is equal to arc cosine 0.9. So by using your calculator, you should be able to work out the angle for this new part triangle. I worked it out. The result is about 25.8 degrees. Still pointing up, okay? So not going down because this is your lagging case. Okay, based on this one, the question is asking us to work out how much, let's double check, calculate the reactive power supplied by this new capacitor. So let's go back here, this triangle. Regarding this red color part triangle, this is a Q prime, right? What is Q prime? Our original circuit diagram will be like this. Voltage supply given the power to the original load Z. But because we want to correct the power factor, so we are adding a small capacitor in parallel with the original load. So this is C, for example. This Q prime in the new part triangle should be the total reactive power consumed by both parts. But this is not the question asked us to find out. The question is asking us to find out, regarding this new capacitor, how much power, how much reactive power is consumed by it. So in other words, the question is asking us to determine this part, the difference between the two vertical edge of the two part triangles. Is that okay, everyone? Any questions? Okay. Regarding how high the green vertical edge is, we have done that in the part A, so that has been solved. So what we need to do is, this question mark is actually equal to the original Q in the green triangle minus the Q prime, which is the vertical edge of the new red color triangle.
Does active power stay the same?
You mean the active power? You mean the real power stuff, right?
Yes.
Must be. Because the question is saying we are adding a capacitor, or capacitors only. Capacitors cannot consume any real power. No matter inductors or capacitors, how many of them you added into circuit, you are changing only the reactive power, not the real power. Is that okay, Ben? Yeah. Okay, this is the idea here. But the calculation should be pretty simple. The first Q, I mean the reactive power in the original circuit should be pretty simple. You have known what is the, I can't remember the numbers. 1 second. So we have got the answers from here. The Q equal to this thing, right? So using the magnitude of the green triangle multiple the original angle. So that's 60 degrees. How much? 375. So this gives us 375 multiple sine 60 degrees. And keep going. This is Q, right? Minus. For the Q prime, how can we derive it? In this case, we have not known what is the new apparent power yet. So we can't use the same way to find out it. But we know what is real power. Real power P, how much is it? I can't remember. 187, thank you. So this doesn't change, right? It's 187.5 watts. So this remains same as the first part. You know the angle is 25 degrees. You know the real power is 187 watts. So the Q prime is actually what? Is using this 187.5 watts. Tangent, yeah. Tangent, 25.8. Is that right? Should be right. The difference between these two Q values is actually the Q values that new capacitor need to consume. Is that okay, everyone? Oh, good? Yeah. Yeah.
So that will give you a positive number, but the amount of bar.
Should be positive. So actually from this diagram, I can see it's positive because the green vertical edge is pretty long, minus a short right edge in the new part triangle, remaining should be positive. Yeah.
Okay, so if it turned out that it was negative.
That means you need to add an inductor rather than a capacitor. Okay. And in such case, Yes, and also if this is the case, I think the triangle is not lagging anymore. So after you use the new path into your circuit, it will be leading. Yeah, it's upside down because you are adding this in to give your side of stuff, okay? But I think the shape of triangle, the power triangle, plus the leading lagging information, plus the angle theta will be just matching between each other. If you just really add some inductor to change the whole thing, and remaining thing is really inductive, so the triangle will just turn upside down. Okay. Okay, this is about our question number 5. Sorry guys, I don't have time to do the detailed calculation. The solution has been given here. Do them by yourself. Okay. Okay, let's move on to the question number 6. So time for now is 1:28. The question number 6 is also single-phase circuit, which is really simple. But the later questions are about 3-phase circuits. I don't want to spend more time on single-phase circuit. I leave this to you. You have the full solution. You should be able to do that by yourself. Okay, all right? So let's move on to the later questions. Let's just focus on the 3-phase one. Of course, for the questions that we didn't discuss in the tutorial part, please feel free to drop me an email if you have any questions. Okay. Okay, let's have a look at the question number 8. This question is pretty long, okay? Now, we got 2 balanced. Highlight this one. Okay, balance is always good condition to simplify our work. 2 balanced 3-phase loads that are connected in parallel are fed by a 3-phase line having a series impedance of 0.4 plus J 2.7 ohms. That means this is just a 3-phase power transmission system. We don't need to really worry about what happened on the source part for now, but regarding the transmission line, there are 3 lines, of course. For each single line, its impedance is 0.4 plus J 2.7. Okay, this is during the transmission. And one of the loads, we can call that as load 1, okay, or load A, whatever. One of the loads absorbs what power is this? Apparent power, coupled power, real power, or reactive power? Yes, coupled power. Rate is unit, is VA. VA is always unit for complete power or apparent power, but these 2 things are similar, okay? So 560K VA complete power. The power factor is 0.707 lagging. And the other load is 132, so what power is it? Kilowatts is always for real power or active power, okay? And at unity power factor, okay, keep going. The line-to-line voltage at the load end of the line is 2200 by square root 3 volts. So please compute A, the line-to-line voltage at the source end of the line. Actually, this circuit should be, the complete view of the whole circuit should be, we may assume at the source part we got a Y connection. I just help you to understand the question, okay? This is the voltage source. And then we have 2 loads. So far, we don't know the connection pattern of the load, but by default, we assume they are in a Y pattern. Okay, so this is the load 1, this is the load 2. My fault. This is just a load A, and 3 phases. Okay, and then this is the load B, 3 phases. We call them as the phase A, B, C, A, B, C, A, B, C phases. And how did they connect them? Okay, we are using 3 transmission lines. The first line comes out from the phase A of the power generator part and goes through a long distance and arrives at the 2 loads, A and B. For B phase and C phase, the same thing. So we give this power from phase B and go to each of these 2 loads, here and here. The very last one, same thing. It looks pretty massive, but the idea is pretty simple, the whole thing. Question, do we need a neutron connection? So here, do we need it? We don't, because the question is saying we got a balanced system. If they are all balanced, no matter what are the phase currents, the summation of them will be cancelled between each other. So the remaining current will be 0. 0 means no current at all. So having or not having the neutral connection doesn't matter. But for you to understand how to use the single phase quantity to calculate three-phase thing, I think make a connection of neutron points should be easier. For example, if I really just make such connection, we said it doesn't matter to have or not have this neutral connection for balance system. We just make it up. And now we got 4 lines. Of course, impedance of the neutral connection is useless because there's no current at all. But by constructing this neutral connection, we should be able to separate this three-phase power system into 3 separate individual AC circuits. Let's focus on one of them. Which one? This one. Can you see that? So I'm using the yellow color to highlight the boundary of one of the 3 phases. Of course, for the other 2 phases, the situations are exact same. The only difference is 120 degrees angle difference. But if you focus on one single phase, this circuit diagram can be simplified to this. This is load 1 phase A impedance. This is load 2 phase A impedance. Of course, the voltage source is now showing up, but this doesn't matter so far. Is that okay, guys? Everyone? Okay. So we do not need to worry about the 3-phase thing anymore because this balance system. We are going to determine the single-phase quantity first, and then use the single-phase quantities to find out the 3-phase thing. Okay. Now let's just examine our conditions. First of all, in the condition of the question, it says the line-to-line voltage at the load end. Be careful, load end and line-to-line voltage. That means, okay, we go back to the 3-phase thing here. Load end means the end close to the loads, so on the right-hand side. The line-to-line voltage means the voltage difference across 2 transmission lines. For example, between the A and the B phase. So such voltage is the line-to-line voltage. But the problem is, we don't need to worry about the 3-phase problems. We want to focus on a single phase. So we can't use this line-to-line voltage directly. We have to use the features of the balance system to convert this line-to-line voltage to a single phase voltage by dividing the line-to-line voltage by square root of 3. Remember last week we mentioned, okay, I draw it quickly, okay? So in the complete plan, for a balanced Y connection load, balanced Y pattern, okay? If we say this is the phase 1 voltage, where is the line-to-line voltage? Line-to-line voltage will be stronger and leading. Make sense? How long will be the line-to-line voltage? That's square root of 3 times stronger than the phase voltage. But the question here is, we have already known the line-to-line voltage magnitude is 2200 square root of 3. So what is the phase voltage? Phase voltage will be using this number divided by square root of 3. So this size is 2200 volts. Okay, everyone? Yeah. So this is why do we need the first step calculation. Of course, this step is calculating the magnitude only with that angle. Okay. And so what's part A is asking us to do? The line-to-line voltage at the source end of the line. The question is asking us this thing. The part A of the question is asking, what is the line-to-line voltage at the generator side? In other words, we want to determine what is such source side line-to-line voltage. Okay. Of course, for this case, we can try to determine what is the source side phase voltage first, and then square root of 3 to get the magnitude of the line-to-line voltage at the source side. Everyone, okay? Are we on the same side? Same page? Okay. So now our task is to determine this thing. What is the source side voltage? But regarding this question here, we have already known what is the receiver side or user side voltage. And we want to determine what's the sending side voltage. The difference between these two sides is just the voltage consumed by the transmission line. In other words, the total voltage supplied by the voltage source or sending end should be equal to the receiving side voltage plus the voltage consumed by the transmission cables. This part, of course, is magnitude 20. Its angle may be just 30 degrees negative. We don't worry about that. So we just need to work out this thing. And then we should be able to work out what is the sending end voltage. But for finding out this voltage drop across the transmission lines, we're supposed to use Ohm's law. Ohm's law says you may use the impedance of the transmission line multiple the current flowing through the impedance. The impedance of the transmission line has been given. So the only question is, what is current given here? So how much current flowing through the transmission cable? Once we know this current, so all the problem will be solved. How to determine this current? Okay, very simple, KCL. In this case here, let's focus on this single phase thing. We want to determine what is current flowing through this transmission cable impedance. At this position, this node here, there are two subcurrents. The first current I1 is flowing into the phase A of the load 1. And the second current is flowing into the phase A of the load 2. If you are able to determine the I1, I2, the summation of these two currents should be equal to the total incoming line current. Is that okay? And then this question is showing that. See here. Where are we? In this case here, I think the question is using power, but doesn't matter. So if you are using the current, KCL should be same. Okay. This question is evaluating what's the total complete power at the load end or the receiving end, like this. In this calculation, there are two terms. The term A here is the total complete power consumed by the first load, and the second term is the total complete power consumed by the second load. Regarding the first complete power here, because we have already known the apparent power for the first load is how much? 560.1 is a kilo VA. This means we are knowing this size for load 1 is such value. And we also know the power factor is 0.707, leading or lagging? Power, lagging means that the direction of the power triangle is correct. So this angle will be 45 degrees, which is just the arc cosine 0.07. Okay, this is corresponding to 45 degrees. So this angle is 45 degrees. Okay, so based on this one, this calculation is showing us, so the complete power at the load 1 is equal to 560.1 multiple cosine 45 degrees plus J 560.1 by sine 45 degrees. Actually, this question is calculating the real component and the imaginary component, real power and the complete power. The reason we have to do that because we need to combine the load 2 things together with the load 1 to get total power. So by then, you have to do the summation. For summation, we have to use such rectangular form to do calculation. Okay, this is the first one. For the second load, the total complete power, how much? For second part, okay. In total, we are consuming 130 kilowatts and no reactive power. So the S2 vector is equal to how much? 132 kilowatts plus J0. Now, these two complete powers for these two loads are all in the rectangular forms. The total complete power consumed by both loads is S equal to S1 plus S2. And you can just add up the two things together to get the total complete power consumed by both loads. And after we know this total power consumed by both loads, So we are going to use S equal to VI conjugate. We know this total complete power. We know the receiving end voltage, so we can work out the current. This current should be total current flowing into both load 1 and load 2. But be careful here, because you are using a single phase voltage and single phase current to do the calculation. Please do not forget to include number 3 here, because this is the total complete power for all 3 phases. But this voltage, this current you are using are the single phase voltage, single phase current. Okay, but we want to know the single phase current for this question, right? So this is what we want to find out. Calculation should be easy. I leave that to you. Okay, so the solution is showing us the result. This current is this current given through this way. Oh, good. Of course, if you want to use the first approach I mentioned, so by using the KCL to add up the I1, I2 to get the I, same result. The calculation is not more hard. Okay. Okay. This is how we derive the current. Once you know current 100 something like that, multiple the impedance of a single transmission line. So this thing is calculating how much voltage drop across the single line transmission. And if we know how much voltage is dropped across the transmission line, plus how much we received as receiver, so summation of the two is the total voltage going to supply at the sending end. This voltage is a single phase voltage at the sending end. And by the end, by multiple square root 3, we are converting this single phase voltage to the line-to-line voltage of the sending end, then finish. Question is not hard, and the key thing for this question is to understand different notations, because we are converting from the line-to-line to phase, phase to line-to-line, again and again. So you need to have very clear mind on what we are doing, and why we can use a single phase to represent the 3 phase, because it's balanced. So everyone, is that okay? Exactly 1:45. Okay, guys, start to say we can't move any further. And after this one, there are a couple of more 3-phase questions, very fundamental. But some calculations given in solution are pretty, brief, and we didn't give you too much explanations. I want you to go through them, and if you have a question, please try to troubleshoot and solve it before we move on to the hard contents. This class, okay, everyone? Oh, good. Thank you for attending this class. And on this Wednesday afternoon, we are going to move on in the second chapter. So within that 3-hour lecture, I will try my best to finish the introduction of the short transmission cable and medium transmission cable models. So hope to see you guys again on Wednesday. Thank you very much for attending this class. Okay, online students, thank you for attending this session. And because the time has been used up, so we are finishing our class now. And if you think there are anything not clear, so please feel free to send me an email. Again, thank you for attending this session, and see you on Wednesday. Bye for now. No worries. Thank you, Jason. Oh, Louis, my consultation time. So I forgot. What is the time for Tyrone? So anyway, Louis, don't worry about that. So let me double check Tyrone's consultation time, and double check is my timetable. And I will send a message on your LMS regarding my timetable, regarding my consultation time. Is that okay? No worries. Thank you very much. Okay, guys, bye for now. See you later.
No, so there's no I'm going to see. They're flying a drone, or you know how we default communication stations. So we've got very low frequencies, but high voltage.
Low frequency, but high voltage.
Yeah. And so we're flying a drone that operates like at 2.4 gigahertz to 5.6 gigahertz, like that's pretty high. And the frequencies are like 19.8 kilohertz.
It's really low.
Yeah.
Yeah.
So they should have no interference whatsoever. Yeah.
No, because that's really separate away between they're very far away
Yeah.
from each other.
So there should be no interference. Yeah.
No. That I can easily found.
Yeah.
So it's 2.45 gigahertz. It's 900 kilohertz. No interference.
But could there be like, because the power lines are such high voltage, could it sometimes, like, could the area around the power line be charged? And if they get too close, it's not going to have electrical.
No, you,
No.
no. That's totally separate. Far away from each other. No,
Yeah.
no interference.
And so like the high voltage won't affect it either, even if you get too close, it's safe.
Yes, it should be safe. I think. I believe so. Yeah.
Yeah, so even
What project you are doing?
it's like civil, they're Duratech, so they're going and they need to, I think they're like it's mainly civil, so they'll be like getting a drone over to look at all the structures.
Roughly, I know that. Yeah, but normally they will not interference with each other.
Yeah.
Yeah, no interference at
So
all.
the high voltage, it won't charge and it's staying quite close to the line and stuff. Yeah, I just want to, it's to do with power and signals.
Yeah, the combination of the two areas.
Yeah.
That should be fun.
Yeah.
No worries.
Thanks,
Okay,
Luigi.
see you.
I love having practice.
Thank you very much. So make sense, right? The class?
Yeah, yeah.
Better than last time. Better than last week. I know. Last week I was a bit slow, but today you can see I'm speeding up.
Yeah.
The speed okay?
Yeah.
Perfect.
Yeah.
Nice. Okay.
Next week.
Don't worry. Okay, see you. 稍微快点，因为我马上有课。
为什么这个是三个 three phase？
为什么说是 three phase？
它是 one of load，one of load一个嘛，
这是两个 load，是两个 three phase load，两个三相组合，其中一个组合
就是那个 load 就是包括三项。
对呀，他说为何我们说的是三项原目啊？所以他说 load 只是说是其中一个整个三项的 load 是做什么？
啊，我以为是三个中的一个。
不，这一般说总的，他说是单项 load，就是那个 single phase load，那可以说。
它这个 one of load 只是说它这
两
个
个 load 中的一
P
个。
和 Q。
啊？
它这个
对，是一个 load 的 P 和 Q，我的那些东西都是。
S 和 P。
一个 S
配 V 一个 P。
S 是给第一个 load 的 S，P 是给第二个 load 的 P。我马上看，我用这个其实反差其实这样，其实很麻烦吗？
我在进入的之前，这张给我的实际原因是三项组合。
不，这单项。和 face 一个 face 是一个对不对？你这个求的什么？是 V2 吧？它这个是总的三项的总功率。但你刚出三公式嘛，你要求三项总功率是 S 是3倍，单项变压成单项变能。所以说你这实际上是你是还没说这样的，你这其实是这边的，就临近它之前总的变能多少？对。
其实还是在这里说的还是
是三项。我们只是把它化简成单项来讨论，但实际上这系统还是三项系统。再来，Yeah, finish. Thank you. 不，我也赶快搞。Okay, thank you very much. See you.